We have now seen how planning problems can be formulated as search problems, and we have also seen a basic algorithm that can be used to solve search problems. We have also already seen some examples of search problems, such as the missionaries and cannibals problem. Now we shall look at some more example problems. The first problem we will look at is a toy problem, and it's a problem that has been around for a long time. The sliding tile puzzle or sliding block puzzle looks essentially like this. What we have is a grid. Here it's a 3x3 grid, and in this grid we have 8 tiles. That is, one square remains empty. We can then shift the tiles in the grid, but of course we can only shift them into the empty slot, leaving another slot empty as a result. The tiles themselves are numbered 1 through 8, and our task is to bring them into the right order, and the right order is showing here on the right, and this could be some initial state from which we start. So to formulate this as a search problem, we have to ask what is the initial state, and the initial state for this problem could be any configuration of the tiles. So not just this one here shown on the left, but really any configuration you can think of. The goal state is usually fixed. Depending on where you look, there are different varieties of what the goal state should be like. This is just one possible state here you see on the right, where the tiles are in the correct order. Sometimes you see the middle square should be empty, sometimes it's another square that should be empty. But there's usually one fixed goal state that must be reached in this puzzle. The actions that are possible, and I've already told you this, are to move a tile that is next to the empty space into the empty space. So I could either move the 8 here, or the 4 up, or the 6 into this empty space. In this case, for this puzzle, there would be 3 possible actions in this state. For the path cost, we simply assume that moving a tile has a unit cost, so all actions have equal cost. So that's it. That's the definition of the 8 puzzle. There are also larger versions of this puzzle on a 4x4 grid with 15 tiles, known as the 15 puzzle, or on a 5x5 grid with 24 tiles, known as the 24 puzzle, and so on. The next problem is also a toy problem, and it's known as the n queens problem in general, but we will look at the 8 queens problem here. And the problem is to find a configuration for 8 queens on an 8x8 chessboard such that none of the queens attacks any of the others. For those of you who don't know chess, a queen is simply a chess piece that can be somewhere on the board, and it can move along any diagonal, any column, or any row. So if we look, for example, at this queen here, it can move anywhere along this diagonal, or this diagonal, or it can move anywhere in its row or anywhere in this column. So you can see this queen attacks none of the other queens and is attacked by none of the other queens. If we look at this queen, however, we can see that if we move all the way along the diagonal, this queen is attacked by this queen, so this configuration shown here is not a solution to the problem. Now, you may wonder how this can be seen as a planning problem, because what we're looking for is a configuration, so a static state. And the answer is that we can look at this as a problem of reasoning about action. When we look at this here, it says we have to place the queens on the chessboard, and we place the queens one after another. So the initial state is the empty chessboard. The actions we have available are placing queens onto the board, and a goal state is any state where the queens don't attack each other. Again, we can assume a unit cost for the actions, so all actions are equally expensive. And I'll give you a hint how this can be formulated a little more efficiently, because if we allow a queen to be placed on any board position, we have 64 different positions, and this would create a pretty big search tree. So what we can do is we say that the first action can only place a queen in the first column, so we can only place a queen here. The second action in our plan must place a queen in the second column, and so on. So our plan will definitely be 8 steps long, and we only have 8 possibilities for each step in the plan. So this defines the n queens problem as a general search problem or as a planning problem. The next problem is more like a real-world problem, and it is the dock worker robots problem, That is also used in the book this course is based on. So you will see this problem occur again and again. The aim with this problem is to have one example that we can use to illustrate many of the techniques and algorithms that will be introduced in this course. The advantage of this problem is that it is not trivial to solve, but it also can be described fairly quickly. The informal description of this problem is this. We have a harbor in which we have several locations, which may be docks or other places. At these docks there may be ships, and we have storage areas for containers that need to be moved around the docks or loaded onto ships. We also have parking areas for trucks that can carry containers, and they will be robots in our cases, or trains that arrive with the containers. There will also be cranes to move the different containers around. They can load containers onto ships or robots, or they can unload them from ships and robots. And what we will be interested in is generating plans for the cranes and the robots that achieve certain configuration of containers that we give as goal states. Now, there are some people who say that block stacking or container stacking, which is essentially the same thing, is not a real-world problem. So this is why I have included this picture here. So this proves that it is a real-world problem. Now, let's look at the state of the world in the Dockworker robot example. What we have in each state are locations, and in this example there are two locations, L1 and L2, and these locations are connected by paths along which the robot, for example, can move. So these two locations are adjacent because they are connected by a path. At each location we have cranes which can be used to move the containers around. They can move the containers between the different piles that are available. And here at this location L2 we see there are two piles, P2 and Q2. In this case they are both empty, there's no containers on these piles, but at the bottom of every pile we will always have a pallet onto which we can stack the container. So the pallet tells us where the bottom of the pile is. A pile itself is an abstract object. It doesn't necessarily need to have anything in it. An empty pile isn't really something we can touch, but it can have containers in it. And containers are of course what we have the most of in most states. So here in this example we have 6 different containers. They're called CA, CB, CC, CD, CE and CF, and they can be stacked on top of each other in a pile, as I've already explained. There is no limit to how high a pile can be, despite the fact that it looks in this picture like the crane can only reach so high, but we will consider arbitrarily high stacks of containers. Finally, what we have in these states are robots. This is one robot here, so there's only one robot. That is an object that can be loaded with a container by the crane, and then once it has a container on it, it can move to a different location. It of course can also move when it's empty to a different location, but there can only be one container on a robot at one time. Also, at each location we can only have one robot at a time. We consider a location occupied when a robot is there. So I think that's pretty much all you need to know about the world states in the Dockworker robot example. But just to clarify this, not all states will have 2 locations and 6 containers and 1 robot. We will consider different worlds with many different numbers of robots, containers, or locations and cranes, and they will give us more complexity to the problem. You can probably guess what the different action types in this domain are, but here they are just to make sure that we are all on the same page and understand what the actions are. The first action is the move action, and the move action moves a robot, that's the first argument to this action, from one location, the second argument, to some adjacent and unoccupied other location L prime. So as a result of this action, the robot will be now in a different location. That other location must be unoccupied and it must be adjacent, which means there must be a path that connects the 2 locations L and L prime. That was the only action that is to be done by the robot. The other actions are all done by the crane. So the first one of those actions is the take action, and we can take a container C with an empty crane K from the top of a pile, and they must all be located at the same location L. So this action As a result, we'll have the crane holding the container, and all these objects must have been at the same location, obviously. The reverse action is to put down the container C that is held by the crane on top of a pile, and they must again all be located at the same location, L. Two more actions, again both to be done by the crane. The one is loading a container, but this will involve a robot too. So what we do is we load a container C that is held by the crane K onto an unloaded robot R. So the robot must not already have a container on it. And again, this must all be at the same location. And the reverse action is to unload the container from the robot. That's the robot. And again, the crane must be empty so that we can do this, and all the objects must be at the same location. So these are the 5 action types that are available in the DockWorker robot domain. Notice that I said action types because there can be many instances of these actions depending on how I instantiate these parameters. So if there's only one robot, then this robot may be the only one that can move, but it can move between different locations, and these are all different actions. We will specify all this more formally when we have introduced an action description language, and that will be next week. And here is a very simple example of what the state transition system that corresponds to the DockWorker robot problem could look like. You can see this is a very simple problem because a large state space wouldn't fit onto one slide. So I had to reduce everything to one robot, one crane, one container, and 2 locations, which gives us 6 possible world states. And they are named here as 0, as 1, as 2, as 3, and so on, as 4, as 5. The objects you see in these states are exactly the things I have just talked about. So we have a robot here, we have a crane, and we have a container, a pallet, and the 2 locations I just talked about. And the actions are in principles also those I've just mentioned, and they give us the state transitions, and we've labeled them here, the state transitions. So the take action gets us from state as 0 to state as 1, and so on. The put action would get us back to that state. We have a move 1 action which moves the robot to location 1, and we have a move 2 action which moves the robot to location 2. As you can see from the state transitions, this system is static, which means there are no events happening. All the actions are under our control. Also, the system is deterministic, which means every action leads to exactly one other state. So there are no 2 transitions from one state that lead to different states given the same action. If we do move 1 in this state, we always get to this state. There's no other option. This is a deterministic state transition system. Like I said before, you will see a lot more about the DockWorker robot problem, so I will stop here. So this concludes this first segment of the course. And here's a quick summary of what we've learned so far. The first question we've looked at is, what is planning? And more specifically, what is planning in AI? And the answer we have come up with is that planning is an explicit deliberation process that chooses and organizes actions by anticipating their outcomes. Planning in AI is the computational study of this deliberation process. Next, we have looked at a conceptual model for planning, which helps us define the semantics of planning problems. To this end, we have defined the state transition system, which consists of 4 things: a set of states, a set of actions, and a set of events, were the first 3 components. And the most complex one is the state transition function, which maps a given state and an action or event to another set of states. Then we have looked at the connection between planning and search. We have seen that planning problems can be phrased as search problems. Search problems can be defined by an initial state, a set of actions that are possible in different states, a set of goal states, and a path cost function that tells us how much the individual actions cost. And finally, we've seen a number of example problems that can all be phrased as search problems.